Hi there, my name is Asa McComb, and I am a physics teacher at Xenia High School and also Dr. Eric Rowley's teaching assistant this semester at Wright State. If you're watching this, that means that you've made the exciting decision to study physics this semester. Congratulations! Um, this is going to be my pre-lecture series. Basically, I'll be making some videos, a combination of both on a tablet and in person to try to help you get ready for Dr. Rowley's lectures. I will be covering a lot of examples and a lot of more basic terminology and demonstrations that will free you guys up to have some more time to work more complicated problems and go a little bit deeper into the content in class. How this is going to work is I'm going to alternate sometimes between being in person and being over voiceover. I'm going to be working some examples, I'm going to be doing some demonstrations, and I'm going to be showing you guys all of the stuff that you need to know from every chapter before lecture. It is expected that you have watched my videos and done the exercises with me together by the time that you arrive at Dr. Rowley's class. Something that I think is going to be helpful is I'm designing my videos to be a little bit Dora the Explorer style, in that every once in a while I will present a problem, pause the video, and then give you a chance to work it yourself. I strongly recommend that when this happens, you do that, pause it, try it on your own, and then watch my explanation and see if you did it correctly. I'm super excited to be working with all of you this semester, and I hope you all have a wonderful time learning about the universe. With that being said, let's get into our first lecture. Okay, what is up, everybody? Uh, it's Digital Asa here, and I'm coming at you from the crunchy audio dimension. Um, Here we're going to be talking about the first chapter in Physics 1110, and also doing a little bit of math review. Uh, I know some of you have probably had a math class kind of a while ago and might need a little bit of refreshing. So we'll do a couple of practice examples at the end to make sure everybody's up to speed on the kind of math that we're going to be doing here in Physics 1110. So without further ado, let's go ahead and talk about chapter 1 of the text. Okay, so here in physics, we're going to be uh, making mathematical models of physical situations. That is the entire purpose of the study of physics. We want to measure things. We want to determine different properties of objects and particles and energies mathematically, and we want to be able to quantitatively just describe the universe. So to this end, we're going to use variables. You guys are all obviously familiar with variables, but I do want to mention a couple of things about them. The first is that capital and undercase letters represent different quantities. So like, for instance, capital V here is volume, lowercase v here is velocity. Lowercase m is mass, you'll see that one pretty commonly. And then often we'll also get Greek letters as well. So only so many letters in the alphabet, and there's lots of things to measure. So often we will use Greek letters to describe different things as well. So this Greek letter theta is usually for angles. This Greek letter capital delta is usually used for meaning change. So like delta V, for instance, delta V would mean change in velocity. And this Greek letter omega means angular velocity. So an object that is spinning around, instead of moving in a straight line, we'll use omega to describe its velocity instead of V. So all that is to say that like we have different symbols that we'll use to mean different things. And sometimes we'll use Greek letters and sometimes we'll use capital letters. We can also use sub and superscripts. Subscripts we'll primarily use to describe the same variable, but with a condition on it. So for instance, often this will be a number or a symbol that represents time period. So like V0 versus V1 versus VF would mean velocity at time 0, velocity at time 1, and velocity at final time. So for instance, if I'm talking about the same object that's moving around, I can describe its velocity at 3 separate instances in time, its speed at 3 separate instances of time, by putting this notation of 0, 1, or f at the end to say, this is what it is at the beginning, this is what it is at some point that I picked, this is what it is at the end. So they're all velocities, so they're all going to be v's, but we can use these sub and superscripts, or sorry, specifically subscripts here, to specify when that velocity is taking place. Likewise, we could also use subscripts to describe a certain type of something. So, for instance, capital F is force, There are multiple different types of force. F sub n could mean a normal force of an object pushing back because of Newton's third law. F of g might be a gravitational force. F of f would be a frictional force. So the subscripts will specify a type or a condition of a variable specifically. So that's the purpose of using a subscript. But the idea is you don't want to have to use a different variable for something that represents a different quantity. So for instance, if I'm talking about a velocity, it's always going to be a v. And to tell my v's apart, I'm going to use subscripts. Okay, cool. Moving on, like I said, physics is the study largely of turning a physical situation into a model. So a model is just a way that we can represent or visualize something that is hard to observe itself. So this means like looking at for instance, like this model here, looking at a physical situation mathematically. So here, this is called a free body diagram. Basically what you do is you take an image with an object on it, and you draw these arrows, these vectors, representing all of the forces that are acting on that object. So, for instance, this is a box on an inclined plane. We have gravity pointing straight down here. That's this FW, or force of its weight. We have friction pointing in this direction. We have normal force from the incline pointing up, and then we have this fraction of gravity being pulled down the incline. Basically, this is a way we can mathematically describe all of the things that are acting on that box. So this is a model of, a box sliding down an incline that accounts for all the different forces acting on it. Likewise, a map of Wright State's campus is a model. I cannot look at the entirety of Wright State's campus without being on a plane, so this model can be helpful in determining where I am relative to other things. I can see you are here and try to determine how to get to whatever building I'm going to using this map. So it's a model. Likewise, an atom, you've all seen the model of an atom classically before. We got our protons and our neutrons here in the nucleus. You got the electrons on the outside. Um, the model of an atom, the Bohr model specifically, is a model. We've never actually seen an atom before. Human eyes have never, looked at an atom and been able to say or determine what it looks like. But based on our experiments, we know that there's a chunk with both positive and neutral particles in the middle, and we know that there are electrons around at different energy levels, which is what these rings represent. So we can take that complicated thing of the atom and boil it down to a simpler model here that represents all of its properties. Likewise, another thing. This is one of my favorites. Here is a model that we have of space-time, a visual representation of gravity's effect on space-time. So basically, we see the universe in 3 dimensions. When you look at the way that space curves as a result of gravity, it's very hard to visualize because we can only see the universe in 3 dimensions. So here we have this representation where we've taken that gravity and represented it as a plane outwards with this sinking in, representing the pull towards Earth. So this is taking something that is happening, in a sphere around the world in 3 dimensions and trying to simplify it by making it something closer to what our brains are able to understand. So all these are models. They're representations to make something simpler. Okay, so there's a couple of pieces we have to do to turn a situation into a model. The first is to establish a frame of reference. So, you often will want to draw a drawing or want to look at a picture of something. It is important for us to determine the perspective we're looking at. So, a good example of this, 3 common ones you'll see are top-down, a side profile, or a POV. Honestly, we usually will just use top-downs or side profiles. POVs are a little bit more rare. And I like to think of this as like, different video games. So like for instance, a strategy game like StarCraft 2, like this, is in the top-down perspective. A side-scroller Metroidvania like Hollow Knight would be something like from a side profile, and a POV would be like a first-person shooter like Doom. So in all 3 of these cases, we have a different perspective that lets us look at our situation and get information about what's going on. It also will determine the rules that we're able to apply here. Like, for instance, I'm not going to need to like aim in a game like StarCraft. I'm gonna, be looking at the top down and commanding units to do stuff. I'm not gonna be able to go towards or away from the screen in a game like Hollow Knight. I'm limited to moving either left or right or up or down. So in each of these cases, in each of these regimes, we're gonna be able to have different rules and different perspectives, and that will make modeling certain situations a little bit easier. We're also going to be establishing a time period. So we're going to look specifically always at a specific period of time where that we care about. Like for what length of time uh, are we going to focus on so that we can solve the specific problem or learn the specific thing we're trying to learn, measure the specific thing we're trying to measure. So a common example of this is like, let's say I'm throwing a tennis ball out of my hand into the ground, or at the ground rather. I think it's blue. Let's say I'm throwing a tennis ball at the ground. Um, and we wanted to look at its motion in the air. Well, the instant before it leaves my hand, it's not uh, falling in a path directed by gravity, so we will ignore that period of time. And after it hits the ground, it gives a lot of its energy away to the ground, so it no longer um, is following that same rule set. So basically, I could look at this model and say, sure, I'm going to evaluate from the moment it leaves my hand to the moment it hits the ground. And I would call this my initial time. I would call this my final time. We'll talk more about that in the next chapter. But basically, my point is we can narrow it down to a specific period of time to focus on the information that we want to focus on. And also, you want to establish objects of interest. So, like, what objects can I care about, and what objects do I not? So, for instance, in this diagram here, this is from our textbook actually. We have this man and this child. He's pulling this wagon with a child in it, and he has a force directed here and a distance directed this direction. In this case, we're going to treat the wagon and child like they're one object, and we're kind of ignoring the ground. We're kind of ignoring, resistance from the air. In this model, we're focusing primarily on this wagon and the forces that are acting on it. So, like, if this man is here, he's applying a force to the wagon, but the thing being moved is what we're focusing on. So we don't need to worry about the forces acting on our guy here. We don't need to worry about the forces acting on the ground. We're just focused on our object of interest. Okay, so let's do an example of this and make a physics model. All right, so here we have an example from the video game Prince of Persia. We're going to be looking at wall running. So this wall running is something that you see in games all the time. It happens in Assassin's Creed too. Some people that are very dexterous can actually do something similar to this, doing parkour. It's very cool to watch. But we're going to try to take this clip and make a physical scenario out of it that we can evaluate. So let's look at that for a moment and then go back. Okay, so here we're going to take that clip that we just watched, and um, we're going to be making it into a model. So let's say, for instance, I wanted to evaluate Dastan's motion as he's climbing along the wall in this clip that we watched from Prince of Persia. So we're in third person. We're looking behind him. I chose this screenshot from that video about 17 seconds in to be the exact moment in time we're going to look at. We can, of course, evaluate different moments in time if we want, but here we're going to focus on one specifically. I'm going to go ahead and draw a free body diagram. So we're going to evaluate the different forces that are acting on this character here at this given point in time and try to get a sense of what's happening from a physics perspective in the situation. So first things first, he has a translational velocity in this direction. So I would draw an arrow in this direction with a V there. And we also have several forces being applied. So we have gravity acting on him, presumably, pointing straight down. So I'd call that F subscript G for force of gravity. We're going to have a force from his legs going into the wall at an angle here. If I wanted to be a stickler also, I could connect these two lines and call this angle theta. There's some angle between the way he's kicking into the wall and gravity pointing straight down. I'm going to call this F DAST for force from Dastan's legs. I could also just as easily call this F legs. What you name your subscripts doesn't really mean as long as you know what you're talking about. So I could call this FL, I could call this F kick if I wanted to, whatever, it doesn't matter. Okay, we also notice that we have a pull. His clawed gauntlet hand thing here is pulling into the wall, grabbing into the wall and pulling him to it. So we have another force, oopsie. This direction, I would call that F claw, maybe, or F pull, or F hand, or something. Just naming that force so I know what I'm talking about. Also, presumably, there's going to be some friction. since we have objects rubbing against each other. So we could, for instance, evaluate our frictional force as um, moving opposite the direction of our velocity. So I could say that my frictional force is kind of like in along the wall here, kind of like in this direction. So I'd call it F for force friction. So anyway, my point is we're able to get lots of different information by looking at a specific point in time. So this would be a model of all the forces of Destin as he climbs along the wall from Prince of Persia. So this is an example of how we can turn a thing we're looking at into a model and then evaluate it. If we were able to assume or measure or calculate some values, we could get more information, right? We could, for instance, look up what the average mass of a person is and try to determine what the force of gravity acting on him is numerically. We could estimate the force of friction between his claw hand and the wall. We could use like a protractor to measure this angle theta here, for instance. So we have lots of options for how we can evaluate this situation, depending on what it is we're trying to measure. So